Welcome to Math TV with Professor V. In this video, we're going to go over homogeneous equations, continuing our video lecture series on differential equations. Definition: if a function f has the property that f of tx, ty is equal to t raised to the n times f of xy for some real number n, then f is said to be a homogeneous function of degree n. T is just some constant, that's what it stands for. And right now we're going to be using this definition to determine whether certain functions are homogeneous. And then we'll talk about what that means for us in terms of differential equations. So, example 1, determine whether the given function is homogeneous. If so, then state the degree of homogeneity. Remember, the degree of homogeneity is whatever n is. So find n. Okay, just go ahead, apply the definition. So for example A, we have f of xy equals rad xy times 4x plus 3y. So f of tx, ty would be equal to rad tx plus ty times 4tx plus 3ty. And then let's try to clean this up and see if we can get back to the form t raised to some power n times our original function. Look here at the radical. I can factor a t out from both of the terms. So let's go ahead and do that. So I have t times x plus y all underneath the radical. And then I can do the same thing over here, factoring out a t. And then I'll be left with 4x plus 3y again. Okay. And then I can break up the radical. So now I have rad t times rad x plus y times t times 4x plus 3y. All right, very good. Now we can group this rad t and t together. So combining, I'm going to have t to the 3/2 power. That's 1/2 plus 1. And then we have rad x plus y and 4x plus 3y. And then lo and behold, this is our original function f of xy. So I can write this result now and say that f of tx, ty is equal to t to the 3/2 times my original function, f of xy. So we've just shown by applying the definition that f of xy is indeed homogeneous. And then we need to identify the degree. And remember, the degree is whatever n is. So the power on t. So it's homogeneous of degree 3/2. All right, very good. Let's look at another example, just so we can get the hang of this definition and what homogeneous functions look like. So here we have f of xy equals sine of x over x plus y. So x over x plus y is the entire argument. If it helps you and you want to add some parentheses here, feel free. So let's go straight for the definition. Don't forget the definition. We want to evaluate what is f of tx, ty. So that's going to be sine of tx over tx plus ty. And notice again, I can factor out a t from both terms in the denominator. So I have tx over t times x plus y. And I can cancel out the t from the numerator and denominator. And now I'm just going to be left with sine of x over x plus y. And that's actually the original function f of xy. So this is interesting. That means f of tx, ty is equal to the original function f of xy. So basically, if we were to apply the definition for a homogeneous function, we would say we could write it as t raised to the 0, correct? Times f of xy. That means this function is indeed homogeneous, okay? But what degree would it be? Can you figure that out? Yes, f of xy is homogeneous of degree 0. Good. Let's box that too. That was an exciting moment for us. All right, let's look at one more example here where we're going to apply the definition. We have f of xy equals natural log of x cubed over natural log of y cubed. So again, just go straight for the definition. F of tx, ty equals natural log of tx cubed over natural log of ty cubed. Now let's see, I want to play around with this so I can try to like break that t out somehow. So let's use our log properties. I can move the exponent on the argument, remember, to the front of the logarithm for both. So I can write this as 3 natural log of tx over 3 natural log of ty. Both those 3's cancel out, they're gone. And then I can expand both the numerator and denominator, again using our log properties, and write this as ln of t plus ln of x over ln of t plus ln of y. And then, I mean, at this point, we're pretty much out of options, right? We can't play around with it or break that t out of the natural log somehow. And I'm looking back at my original function, and it doesn't look like there's any way I'm going to be able to write this expression as t to the n times ln of x cubed over ln of y cubed. It's just not going to happen. So what does that tell me? That tells me that f of xy is not homogeneous. Okay. Good. Now, in some more basic cases, if the function isn't too complicated, you can test another way by figuring out the degree of each term, which I wanted to show you here. So example D, we have f of xy equals 6xy cubed minus x squared y squared. So I want to figure out what the degree of each term is. So look at the first term, 6xy cubed. Think back to your algebra or pre-calc days. So the power on x is 1, so it's degree 1. The power on y is 3, so it's degree 3. And we say overall this term is degree 4, right? If you add up all of the powers on the variables, all the exponents on the variables. Now look at the next term in the function, x squared y squared. Again, let's figure out the degree of each of the variable components. So x squared, that's degree 2. Y squared, that's also degree 2. So overall, this term is degree 4. Now, since both the terms in this function have the same degree, then we say, all right, f of xy is indeed homogeneous of degree 4. So you could check again using the definition, but this is just a quicker way to do it if you're working with a more simple function. Okay, the examples I did previously were a little more complicated. Okay, one more like this. F of xy equals x squared minus y. So notice here, this term is degree 2, x squared. Y is to the first, so that's degree 1. And this function is not homogeneous. Why am I saying that? Because the degree of the two terms is not the same. So the degree of the two terms is different. Very good. Now, as a note, if a function is homogeneous, then it has a special property. So if f of xy is homogeneous of degree n, then we can write the following. So we can write that f of xy is equal to x raised to the n, the degree of homogeneity, times f of 1 comma y over x. And similarly, we can write f of xy as y raised to the n times f of x over y comma 1. This is going to be important when we go to solve homogeneous differential equations in a hot second. So just remember this. Okay, very good. So now we've identified what homogeneous functions are. Let's build on that and look at homogeneous differential equations. So a differential equation of the form m of xy dx plus n of xy dy equals 0 is said to be homogeneous if both coefficients m and n are homogeneous functions, now be careful, of the same degree. Okay, so a homogeneous differential equation will have two homogeneous functions in it, and the degree needs to match. One homogeneous function m is multiplied by dx, the other one n is multiplied by dy. All right, and notice that means we could write the homogeneous differential equation as follows. M of xy dx plus n of xy dy equals 0 means I can write it as m of tx ty equaling t to the n times m of xy, and n of tx ty equals t to the n times n of xy. So same degree, m has to be the same. All right, let's go ahead, look at an example where we're going to check if the following differential equation is indeed homogeneous. So notice here we have 2 rad xy minus y times dx minus x times dy equals 0. So I'm going to first identify what m of xy is and what n of xy is. Remember, you have to get this form in your memory. M of xy dx plus n of xy dy equals 0. Okay, so let's color code. There's m of xy, it's the 2 rad xy minus y, and then here's n of xy, that negative x. So we have to do 2 tests to check if m of xy is homogeneous, and if it is, what its degree is, and then again for n, and make sure that the degree matches. Okay, so m of xy is equal to 2 rad xy minus y. You can totally do the test where you're just checking the degree of each term. I'm going to apply the definition just so we get more practice using it. So m of tx ty equals 2 times rad tx times ty minus ty. Now let's see, underneath the radical, I'm going to have t squared xy minus ty. And then I can simplify, take that t outside. So I have 2t rad xy minus ty. And notice now I can factor out a t from both those terms. So I have t times 2 rad xy minus y. And voila! Isn't this, oops, I meant to highlight, not scribble. Isn't this my m of xy? Why, yes it is. So this is equal to t times m. So it's homogeneous of degree 1, since t is raised to the first power. And we could have known that from the very beginning, because notice y is raised to the first, so that term is degree 1. And then both x and y are each raised to the 1/2. 1/2 plus 1/2 is 1. Okay, very good. Now let's test n. So n of xy is equal to negative x. Maybe you can tell already. Boom, it's degree 1, right? Done. Let's use the definition. Let's get that extra practice in. N of tx ty. There's no y's in there. No problem. So you just have negative tx, which is t times negative x, which is t times my original function, n of xy. So it's degree 1, just like m of xy. So to summarize, notice both m of xy and n of xy are homogeneous of degree 1. That's important, which means that the differential equation is homogeneous. All right? Very good. Okay, so where's this all headed? Well, don't you want a way to solve these differential equations, these homogeneous differential equations? I'm sure you do. So here's the method. I'm going to walk you through the steps, and then we'll solve a couple examples so you can get the hang of it. And it's a pretty repetitive process. So after you do a few homework exercises, you'll get pretty used to it. Here's the method of solution. You're going to make a change of variables, a substitution. You're either going to substitute y equals ux or x equals vy, which would then make u and v the new dependent variables. Well, either u or v. Then the equation's going to reduce to a separable first order differential equation, which we've already gone over how to solve. So here's how basically the process would work. Just to do a general example, I will use the substitution y equals ux. So let's substitute y is equal to u times x. Now I need to figure out what the differential dy is going to be so I can make this change of variables. And when I find dy, notice I have to apply the product rule. So differentiating u times x, I'll have u dx plus x times du. So I'm going to replace dy with that entire expression. So remember, we start with m of xy dx plus n of xy dy is equal to 0. And now let's go ahead and make our change of variables. So I'm going to have m of x. Instead of y, I'm going to have ux dx, that stays the same, plus n of x, again, instead of y, now we have ux, and then instead of dy, I'm going to substitute in now u dx plus x du, and then this all is equal to 0. Okay? Good. Now, since the differential equation is homogeneous, then that means we can write the following. And you'll see that this step will be a little bit different, which depending on the function, but the general principle will remain the same. You can factor out x raised to some power depending on what the homogeneous equation looks like. So I can rewrite this now as x to the n times m of 1 comma u dx plus x to the n times capital N of 1 comma u, and then I still have u dx plus x du equaling 0. Okay, remember that was that property of homogeneous functions that we went over previously. What do I do from here? Well, I'm going to divide by x to the m. Now be careful. Anytime you're dividing by a variable, you have to assume that the variable does not equal 0 and then consider the case if it were to afterward. So for now, we'll talk about that in a second. I'm just going to assume x does not equal 0, all right? And then divide this differential equation by x to the n. And then now I'm just left with m of 1 comma u dx plus n of 1 comma u. And then let's just go ahead and distribute while we're at it. We can handle it. Times u dx plus n of 1 comma u x du equals 0. Now what I want to do is group the terms that have dx's together. So I can write this as m of 1 comma u plus u times capital N of 1 comma u dx plus, and then what's left over is right here, I have x times n of 1 comma u du equaling 0. And maybe now you can see, all right, this differential equation is now separable. So I can go ahead, divide out everything. So we'll have dx over x plus n of 1 comma u du over m of 1u plus u times n of 1u equaling 0. Okay, and then it's separable. Move one of them to the other side, integrate both sides, bada bing, bada boom. So to get from this line to the last one, I just divided everything. I didn't want it to get too messy. Just divide everything by m of 1 comma u plus u times n of 1 comma u and divide by x. Okay, that doesn't quite fit in there, so I'm not writing it out. That's what happened. Now, we talked about assuming that x was not equal to 0. What you want to do after you solve your differential equation is just check if x equals 0 is a solution to the differential equation, and if so, then list it separately. It's considered a trivial solution most of the time, so a lot of textbooks won't even bother to check or include it, but technically it will be an additional solution. Other thing is, earlier I mentioned you can make the substitution. Do you remember we had two options? Y equals u times x or x equals v times y. How do you know when to use each one? I'll give you some tips. So when to use x equals vy versus y equals ux. So whenever m of xy is simpler than n of xy. Okay, so if the homogeneous equation that's multiplied by dx looks simpler than the one that's multiplied by dy, then it's a better idea to use x equals vy. Also, another way to know to switch which substitution you use is if you get stuck. So if you get stuck integrating, I guess with whichever one you happen to choose. So if you get stuck integrating with y equals ux, then try the other substitution. Okay, so a lot of the time it'll come with experience, or both could work, you know, just one might be a more brutal integration to solve. Okay, are you guys ready to solve some? I hope so. It's been a lot of build-up, right? Here we go. So example, solve the differential equation by using an appropriate substitution. Now, if you're doing this out of a textbook, most likely you're in some section that's only gonna give you exercises involving homogeneous differential equations. But let's say you're taking an exam at the end of the semester and it's just potpourri of differential equations, you gotta learn to check what kind it is before you get going. So you apply the correct solution technique. So I'm always gonna check. I'm just gonna count the degree of each term, right? So if this is m of xy, degree of all the terms, y squared degree 2, y times x degree 2, okay. This would be n of xy, negative x squared, that's degree 2. So yes, this differential equation is indeed homogeneous of degree 2. Okay, so let's go ahead and make our substitution. I'm going to, notice m of xy, that looks messier than negative x squared. So I'm going to substitute using y equal to ux. And then that means dy would equal u times dx plus x times du. Now let's substitute that into the original differential equation. So instead of y squared, I'm going to have u squared x squared plus, I'm replacing y with ux and then times another x, so that's going to be ux squared dx minus x squared, and then instead of dy, remember we're replacing it with u dx plus x du. And this all is equal to 0. How are we doing so far? Good? All right. Now let's clean things up. Notice I could take an x squared out of here. So let's go ahead and do that. So we have x squared times u squared plus u dx minus x squared times u dx plus x du is equal to 0. Now this next step is kind of that one where you have to be careful. So I'm going to go ahead, divide everything by x squared, assuming x does not equal 0. At the end, we're going to check if x equals 0 is also a solution to our differential equation. So now this is gone, and all I'm left with is u squared plus u dx minus u dx minus x du equals 0. Now I should be left with a differential equation that is separable, all right? Let's group all the terms together that have a dx. So there's u squared plus u minus u. So we've got u squared plus u minus u dx. And then let's just move the x du to the other side. And then these u's cancel out here. And I have u squared dx equals x du. Can you see how this is going to be separable? I hope so. I can divide everything by u squared and x. And then now we have dx over x equals du over u squared. Whew! All right. Now the fun begins. If you weren't having fun already, I'm so sorry. So let's integrate both sides. Left-hand side, antiderivative of 1 over x. It's going to be natural log of the absolute value of x. I'm going to hold off on putting the constant, right? Let's just put it on the right-hand side. Antiderivative of 1 over u squared. Remember, that's u to the negative second. So add 1 to the exponent. Now it's u to the negative first, and I have to divide by negative 1. So this is negative 1 over u, and I'll put the plus c over here. Okay? Very good. Now we have to rewrite our solution in terms of the original variables, which were x and y. So remember, the substitution that we made was we let y equal u times x. That means u is equal to y divided by x. So what we're left with is, on the left-hand side, we still have natural log absolute value of x equals -1 over, and u is y over x plus c. All right, good. Let's clean this up just a wee bit more. So we've got natural log absolute value of x equals, now this is going to be -x over y plus c. I want to multiply through by y, so we don't have any variables in the denominator. And our result is going to be y times natural log of the absolute value of x equals -x plus c times y. Can we do any better? Let's just move that -x to the left-hand side so it's positive, but it's not looking like we can really isolate y or do anything else with this differential equation solution. So we have x plus y natural log absolute value of x equals cy. Boom. So here's our solution. Now, we talked about what if x equals 0. I want to check if that is going to be indeed a solution. So remember, the original differential equation was y squared plus yx dx minus x squared dy equals 0. If x equals 0, then that means dx is also equal to 0. So you would have y squared plus 0 times 0 minus 0 dy, and yep, that's the solution. It's just trivial. So most of the time it's omitted, okay? But if we're going to be very technical, then when you list your solution, you should say x plus y natural log absolute value of x equals cy, and also the trivial case x equals 0. So check with your instructor. Like I said, most textbooks don't even bother to include it, but my differential equations professor was very particular and very thorough, so that's how I was trained, okay? Good. For the rest of the examples, we won't include it, but I wanted you guys all aware. Okay, let's look at another one, a little fancier. So example B, we have y plus x cotangent of y over x dx minus x dy. So let's see. Here is m of xy. Is it homogeneous? Yes, it's degree 1. That looks good. This is n of xy. Is that homogeneous of the same degree? Yep, it's degree 1. So we checked. Everything's good. Homogeneous of degree 1. Which looks simpler, m of xy or n of xy? I say n of xy, so that means we're going to use the substitution y equals ux like last time. So dy is going to equal u dx plus x du, and then let's go ahead and make our substitution now. So instead of y, remember, we're replacing that with ux plus, I have x times cotangent of ux over x dx minus x stays the same, and then instead of dy, we have u dx plus x du equals 0. Okay, let's see how we can clean this up. So notice these x's can cancel. Again, we're assuming x is not 0. What else can we do? I can factor out an x right here. So let's go ahead and do that. So we've got x times u plus cotangent of u dx minus, I'm going to go ahead and distribute the negative, okay? And I factored that x out already, don't forget. U dx minus x du is equal to 0. Okay, canceling out the x there, assuming x is not 0. And in fact, it wouldn't even be a solution to the initial differential equation because it wouldn't make it undefined. So we don't have to include that this time. Let's see what we have left. So where's everybody that has a dx on it? U plus cotangent u and then a negative u, right? Group them together. U plus cotangent u minus u dx. And then let's move that x du to the other side. Again, these u's cancel out. The process will get repetitive after you do enough examples. So you should start to get comfortable. And then we have cotangent u dx is equal to x du. And now let's go ahead and separate our variables. So we have dx over x is equal to du over cotangent u, but I'm going to rewrite that. That's tangent u du, right, people? Good. Let's integrate now. So left-hand side, integrating 1 over x, we're going to have natural log, absolute value of x, equals, and then antiderivative of tangent u du, that's going to be natural log, absolute value of secant u plus c1. Okay, we have some cleaning up to do, so I know my constant's going to change. Now it's time to get back to the original variables that were in our differential equation. So remember, we used the substitution y equals u times x. That means u is equal to y divided by x. All right, so we're going to substitute that back in right here. Left-hand side's the same for now. So we've got ln, absolute value of x, equals ln, absolute value of secant y over x plus c1. Good. How can we clean this up? I'm going to move the ln of secant y over x to the left-hand side so we can use some log properties, okay? So we have now ln absolute value of x minus ln absolute value of secant of y over x is equal to c1. And then using some log properties, I can write this as ln absolute value x over secant of y over x equals c1. And then why am I leaving that poor secant in the denominator? I can rewrite this even more beautifully if I make it cosine in the numerator. So this is x times cosine y over x, yes, equals c1. Okay, so now I've only got one log, nice cosine. Let's rewrite this in exponential form, yeah? So we have e raised to the c1 equals absolute value x times cosine of y over x. If I drop the absolute value, then that means I have plus or minus e to the c1 equals x times cosine y over x. So let's just call this some new constant c, okay? And then we can write our final solution as follows. So we have x times cosine of y over x equals c. And then if you want to specify for anyone, you would say where c is equal to plus or minus e to the c1. My differential equations professor was super precise. Like, he would make us specify that in this case, c could be any real number, because e to the c would only be positive. Negative e to the c would only be negative, you know, so now we're including everything. All right, very good. How was that one? Favorite one of the day? I got one more for you. We're going to solve a homogeneous differential equation with an initial condition. So we're going to solve for the constant c. Okay, so we've got x plus rad y squared minus xy dy dx equals y, and they're also telling us y of 1/2 equals 1. Now you might be saying, wait a minute, this does not look like a homogeneous differential equation. It's not in the form that I remember. Well, we got to separate the differential dy from dx, okay? So just think to yourself, the homogeneous equation form that we've been looking at, they're always set equal to 0. So I'm going to subtract y to the left-hand side, okay? And we have dy over dx minus y equals 0. And go ahead, just multiply everything through by dx. So separate that differential, okay? We have x plus rad y squared minus xy dy minus y dx equals 0. Now this is a little flip-flopped, right? Normally we have m of xy dx, so that's your m of xy. And then we have n of xy dy right here. Which one's simpler? I say m of xy is simpler, right? This is the first time it's happened. This one is simpler, so I'm going to opt for the other substitution. Let's use the substitution x equals vy, okay? Good, I wanted to do one for you like this so you could see how it would work. Pretty similar. You have to start off finding dx, okay? So dx, again, product roll time, v dy plus y dv. And then we're going to go ahead and substitute that in to our differential equation. So instead of x, I'm going to write vy plus radical, instead of y, oh no, y squared stays, come on, minus xy. Xy is going to be vy squared, dy stays, minus y stays, and then instead of dx, we have v dy plus y dv equals 0. All right, very good. Let's see, what can we factor out? So we've got vy plus radical y squared times 1 minus v. I can take out that y squared dy minus y times v dy plus y dv is equal to 0. Okay, I can take a y out from all the terms, right? Rad y squared, I can factor that. So let's pull out a y from everything, and then we're left with v plus rad 1 minus v dy minus, let me go ahead and distribute now, okay, that negative, minus v dy minus y dv, and this is all equal to 0. Okay, good. Now, canceling out the y or dividing by y, that's gone. Let's group everything that has dy together. So we've got the v plus rad 1 minus v and a minus v, grouping all that together. V plus rad 1 minus v dy, and then let's just move the negative y dv to the other side, so now it's positive y dv. What's next? Yes, the v's cancel. That's happened every time so far. And then we've got rad 1 minus v dy equals y dv. Woohoo, now it's separable. So we can write this as dy over y equals dv over rad 1 minus v. And then I'm just going to rewrite this side now as 1 minus v to the negative 1/2, just so it's easier when we anti-differentiate right now, dv. Okay, so let's go ahead. We're going to integrate both sides. Left-hand side, we've seen this every single time. Oh my goodness. Natural log, absolute value of y equals. Okay, Hopefully you can do this integral in your head, right? You shouldn't have to use sub at this point in your math career. Take the exponent, add 1. Now it's a positive 1/2, right? Divide by that new exponent. So you're going to have a 2 in the front. 1 minus v to the positive 1/2. But notice inside we have 1 minus v. So since there's a negative sign in front of the v, I also have to divide by that negative in my antiderivative plus c. Okay? Good. From here, we're done integrating. I want to go ahead and replace v with the original variable. So remember, we made the substitution, let x equal vy. So that means v is equal to x divided by y, right? Good. So we've got ln, absolute value of y, equals -2 times, let's switch back to radical, 1 minus x over y plus c. Okay, lovely. I recommend solving for c at this step, and then we'll clean it all up in a second. So remember, they told us that y of 1/2 is equal to 1. So that means you're going to plug in 1/2 for x, 1 for y. So we have ln, absolute value of 1, is equal to -2 times rad 1 minus, this is 1/2 over 1, so just 1/2 plus c. Well, ln of 1, that's just 0, equals -2 times the square root of 1/2 plus c. Okay, so that means c equals, let me move this over to the other side, +2, rad 1/2 is 1 over rad 2. 2 over rad 2 is just rad 2. So that's what c is. And then now I can put everything together. So remember, we got up to this step. I'm just going to replace c with rad 2 and call it a day. So we've got now as our solution natural log absolute value of y equals -2 times radical 1 minus x over y plus rad 2. And that's it, folks. How was that? I know it's not the cutest solution I've ever seen, but it is what it is. So I hope you found the video helpful. Give it a thumbs up. Be sure to subscribe if you haven't already. I have more differential equations videos coming your way. And share this video with whoever you think would enjoy it or find it helpful. Classmates, neighbors, friends, mailman, who knows. All right, stay tuned and have a good one, guys.